welcome back. We are discussing the forecasting methods in a supply chain environment, and so far we have discussed different types of time series analysis methods. We have discussed about the simple methods where we are taking simply average of the past data, and on the basis of that average we are determining the forecast for the coming periods. Then we also discussed about the limitations of those average methods, and we discussed about smoothing methods where we considered that demand is fluctuating about a base value, and in those smoothing methods we discussed with some type of very fundamental method where there is no type of characteristic available in our demand data. We started with basic exponential smoothing model in which only there are fluctuations around a base value, a level value. Then in our last session we discussed a slightly more complicated model where some kind of trend was also available in our demand data, and with the help of trend and base we actually determined the forecasted value for the coming period. Now we are moving to a more complicated model where seasonality is included in our demand data, and here we have seen in the last class that some data is available to us where we are saying that ratio seasonality is present in this demand data. We discussed in the last class that it is almost impossible from the naked eye to determine the type of data which is available with us. The second column in this table represents the actual demand of 2016 for various months, and for 2017 from January to July. Now from this data it is almost impossible that somebody can say there is no component, it is a horizontal demand data. Somebody can say this data represents trend as well as seasonality, and now I am claiming that this data has ratio seasonality. So for this purpose, that whether this has ratio seasonality, should we use the ratio seasonality model, should we use the trend model, should we use the trend with seasonality model, we discussed in our last class that there are different types of forecasting error measures, and out of that we discussed MAD, that is mean absolute deviation. This is the most important measure which helps us in selecting the appropriate type of forecasting model. We discussed the procedure to calculate the mean absolute deviation. We discussed other type of forecasting error measures also like average error. We discussed MSE, that is mean squared error, and then we also discussed about MAPE, which is mean absolute percentage error. But out of various types of forecasting error measures, we said that MAD, mean absolute deviation, is the most important type of model, is the method which helps us in determining the appropriate type of model for the forecasting purpose. And at the same time, since we are talking of smoothing methods, there are smoothing constants alpha, beta, gamma. What should be the appropriate values of alpha, beta, gamma, that will also be determined using these methods of forecasting error measures. But along with those methods of forecasting error measures, we also have one more measure which will help us in deciding whether the model which we are using, this model has any kind of biasness or not. Now the meaning of biasness is that this is the actual demand 1925, 1921, etc., etc. Now if continuously, if I over forecast, my demand is always less than the forecasted value, or vice versa, demand is always more than the forecasted value. So in both these cases I will say that my forecasting model has some kind of biasness. Either I am regularly over forecasting or I am regularly under forecasting. In a good forecasting model, in a appropriate forecasting model, we should have a fluctuating kind of situation. Sometime I may over forecast, sometime I may under forecast, so that the net story should be more like the concept of average error, it should be on a zero side. So, that is one thing which is determined with the help of one more concept which is known as tracking signal. Now, this concept of tracking signal will give you fair idea. This concept of tracking signal will give us the fair idea whether our forecasting model is moving in one direction or it is a balanced kind of model. Now, to understand the calculation of forecasting this tracking signal in case of forecasting, this tracking signal is calculated as RSFE divided by MAD. RSFE, this stands for running sum of forecasting error. MAD we have already discussed in the last class, that is mean absolute deviation. So, we need to calculate running sum of forecasting error and MAD, and with this ratio you can calculate the tracking signal. Now, I can demonstrate you a sample calculation of tracking signal, and then with the help of tracking signal calculation we will also understand the physical significance of the biasness of the forecasting model. So, now let us have a very simple calculation of tracking signal. You can have the real time calculation also. The reason of discussing this tracking signal in this class is so that because we are discussing the real time decision making, the concept of tracking signal will help us in improving or in adaptive the forecasting model in the real time situation. So, this tracking signal calculation which is I am showing you for a sample data, let us have 6 periods, and for each of these periods let us forecast, let us assume some forecast value that I am forecasting 1000 units for each of these periods. Now, the actual demand for these periods, let us assume some values of the actual demand for these periods, and these demands may be 950, 975, 1050, then again 950, 1025 and 1100. Let us say these are the demand values of over the period. Now, with the help of these forecasting values and the actual demand data, I can determine my forecasting error, which is actual demand. This is column number 1, this is column number 2, this is column number 3. So, forecasting error will be column number 3 minus column number 2, that is my column number 4. Now, 950 minus 1000, this is minus 50, 975 minus 1000, this is minus 25, 1050 minus 1000, this is plus 50, 950 minus 1000 again minus 50, 1025 minus 1000 plus 25, 1100 minus 1000 plus 100. So, these are the forecasting errors. The absolute values of the forecasting error, or you can say this values will be without sign. So, these are 50, 25, 50, 50, 25 and 100. Now, the next column will be running sum of forecasting error, that is my column number 6. The running sum of forecasting error is actually the summation of various elements of column number 4. So, this is minus 50, then you add minus 25 into this, becomes minus 75, you add 50 into this, so that is of plus sign. So, minus 75 plus 50, it becomes minus 25, then further minus 50, it becomes minus 75, plus 25, it remains minus 50 and plus 100. So, it finally ended up with plus 50. So, these are running sum of forecasting errors. Then you also calculate with the help of these ET values your MAD, that is your column number 7. Now, what is the MAD? MAD is actually this ET divided by the number of periods. So, as you go up, you need to add up the values of absolute values of forecasting errors. So, here it is 50 by 1, 50. In the second case, it is 50 plus 25, that is 75, and 75 divided by 2. So, it remains 37.5. Then in the third case, 50 plus 25 plus 50, it is 125 divided by 3. So, it remains like 41.6. Then in the next case, 50 plus 50 plus 50 plus 25, 175 divided by 4. For the fifth period, it will be 175 plus 25, that is 200 divided by 5, that is 40, and for the last period 200 plus 100, that is 300 divided by 6, that is 50. So, you get the values of mean absolute deviation in column number 7, and then in column number 8 we calculate the values of tracking signal, and that will be determined by dividing the values of column number 6 with the values of column number 7 respectively, and minus 50 divided by 50, you get minus 1, minus 75 divided by 37.5, you get minus 2, then minus 25 for third period divided by 41.6. Here the value is again in minus, but it is somewhere less than 1, and we can have the fine tuned calculations also. For the fourth period, it is minus 75 divided by 175 by 4. For fifth period, it is minus 50 divided by 40. For the sixth period, it is 50 divided by 50, that is 1. So, now you see, you started tracking signal from the first period, that is minus 1, it increased to minus 2, then it decreases, it remains only about 0.5, obviously off with the negative sign. Here also it is in the negative sign, here it is slightly more than 1, minus 1, and it is coming plus sign in the sixth period. So, if I plot the values of tracking signal on a graphical plane, so this is time, and on the x axis we have the values of the tracking signal. So, if this is the first period, second period, third period, fourth, fifth, sixth, like this. So, for these periods we can start with minus 1, minus 2, and then in the third period it is coming very close to 0 value, and then in the fourth period it is actually 75, 300 divided by 175. So, it is around 2 minus less than minus 2, it is around minus 1, and in the sixth period it is crossing 1 and it is becoming plus 1. So, you see, you have some type of fluctuations, though all the fluctuations are in the negative side. From period 1 to period 5, you have all fluctuations which are in the tracking signal, but there are fluctuations. Sometime it is going to minus 2, sometime it is coming to 0.5 values also, and then in the sixth period it is coming to plus 1. So, here we can say the forecast sometime is overestimated, sometime it is underestimated. So it is a more like a reasonable forecasting model. But if it is like this, where you have continuously this type of data, if you have this type of data which is represented by these red dots, where your forecasting model is giving you tracking signal which is represented by these red dots, that means you are all the time moving into negatives, and this means you are all the time doing the over forecasting. The red data, this red data is a symbol of over forecasting. Your demand is not that much, but you are doing over forecasting. On the other hand, if you start in this fashion and then you move this way, the dots representing the green line, if this type of tracking signal is there, where continuously the value of tracking signal is moving upward, so this type of tracking signal is representing underestimation, where I am forecasting less, the demand is more, and the physical significance is that I am not able to fulfill the demand of the market. Some of the demand I am not able to fulfill, my service level is low, and as a result of that the customer satisfaction is also low. When I am doing the over forecasting, it means I am piling excessive inventory in my supply chain. I am keeping more inventory in my supply chain which is not required, because I am not touching that level of demand which my forecasting is suggesting, and as a result of that this excess inventory in my supply chain has eaten away my profits. So both these lines which are represented by green or by red are not desirable. My line ideally should fluctuate about this x axis, about the time axis. The still, if you see this blue line, the line which we got as a result of this data, that line is still acceptable, because there are certain fluctuations in this line. But if fluctuations are not there, we will not be able to accept, or we will say that our forecasting model has some type of biasness, and that is not desired. So for that reason, this tracking signal is a very important tool. It is a very important, you can say, outcome which will help us in determining whether the model is having some kind of biasness or not, and therefore this concept of tracking signal must be used in combination with the errors, forecasting error measures, particularly MAD, and tracking signal gives you the biasness. And since we plot this tracking signal in real time environment, so this tracking signal data will help us for any kind of adaptation of the data. If we require any kind of adaptation, this tracking signal will help us that you can modify your model, you can develop your model, you can take care of whatever happening in your recent data, so that your model does not exhibit any kind of biasness. And with this, now we are coming back to this original problem which we started, and now let us see how to go ahead with the solution of this model. So we were talking of we right now, just for the sake of understanding, have just assumed that the model or the data is showing the ratio seasonality, it is exhibiting the ratio seasonality, and with this assumption we are going ahead to understand the process of solving this ratio seasonality model. Now in this particular case, this model needs to be deseasonalized first. Whenever we have a seasonal data, we need to deseasonalize that, and for that purpose, as we discussed in the last class, we first need to take the average of past demand. So in this case we are taking only 2016 data for the purpose of initialization of the solution process. We are not taking this 2017 data to start the solution process. I am taking only the first 12 cells for starting the solution process. We will take the average demand of 2016, and the average demand will be the sum of actual demands of 2016 divided by 12, and that comes to be 24.07. So, this is the average demand for 2016. Now, we will divide the actual demand of any period like of January 2016 19.36 by the average demand, and that will give me the seasonal index. So, like we have shown the sample calculation here, the actual demand of January 2016 is 19.36 divided by the average demand. I got the seasonal index as 0.804, and so on. We do this calculation for all the months of 2016 from 0.804 to 1.128. So, all these seasonal indices are calculated by dividing the actual demand, these actual demands, by the average demand of 2016, that is 24.07, and students can try these calculation to get the seasonal index. Now, these seasonal index of lot of significance, because these seasonal index will be used for calculating the forecast for the 2017. So, we discussed the development of the formula for seasonal index, and now with the help of these seasonal index and the base values, we will determine the forecast for the 2017. You already have the data up to July 2017 in this table. So, we will like to determine the forecast for August 2017, and to determine the forecast for August 2017, in our last lecture we discussed how to develop the formula, and now we are directly showing you the developed formula which we saw the procedure in the last lesson. So, this forecast will be the forecast for August 2017, which is represented by Ft, 1. Ft represents the current period. So, current period is July 2017. So, comma 1 means one period ahead. So, that becomes August 2017. So, I am forecasting for August 2017, and today I am in July 2017. So, I will be using updated base for July 2017, which is represented by St bar, that is the updated base value in July 2017 of to July 2017, and this I t minus L plus 1, this L represents the period of seasonality. L represents the period of seasonality. In this data, you have monthly data for 2016. So, you have the demand data available for each month. So, in this case, the period of seasonality, since monthly data is given, is 12. Sometime you have quarterly data available to you. So, in that case, period of seasonality L will be 4. If you have half yearly data available to you, in that case the period of seasonality is 2. So, L will be 2. So, depending upon the type of data available to you, L will be, in case of half yearly data it will be 2, in case of quarterly data it will be 4, and in case of monthly data it can be 12, and even if you have fortnight data, L can be 24 also. So, depending upon the type of data available to you, the values of L will change. So, if weekly data is available to you, so in case of weekly data L can be 52 also. So, depending upon, since we are considering the monthly data, so L is 12. Now, this formula says T minus L. So, if I am talking of July 2017, so T minus L will be July 2016, and plus 1, it means August 2016. So, for forecasting in the month of July 2017 for August 2017, I am going to use the base value of July 2017 and the seasonal index of August 2016, and their multiplication will give me the forecast of August 2017. And for this purpose, I require two things. One is the updated base value of July 2017, which I am going to calculate from this formula, and second is IT minus L plus 1, which is the seasonal index of August 2016. So, that seasonal index of August 2016 is already available to me, that is 1.178. The updated base value of July 2017 is not available to me. So, that I need to calculate, and once I multiply this value, whichever will come here, with the value of August 2016 1.178, that will give me the forecast which I will put here for August 2017. So, this value which I need to get here multiplied by 1.178, that is the seasonal index of August 2016, will give me the forecast of August 2017. Now, for that purpose, for getting the updated base value of July 2017, I will use this formula. Now, in this formula you see what I am taking, since this is the base value. So, here dt upon IT minus L, this represents again the deseasonalized demand of of July 2017. So, I will, whatever dt is the actual demand, when I divide this dt by seasonal index factor, I get the deseasonalized demand, or you can say the base value. So, whatever is the current base value and then whatever is the previous base value one period before. So, I will take a part of that and I will take a part of that. So, that alpha is the smoothing constant. A smoothing constant multiplied by the deseasonalized demand of July 2017 multiplied, then you have the addition of ST minus 1. The remaining component comes from the base of June 2017. So, if I see from this table, I take this value 30.0273, this is ST minus 1, this is ST minus 1, this is DT 29.14, this is DT. This DT will be divided by 0.988 to get the my deseasonalized demand of July 2017. 29.14 divided by 0.988 multiplied by alpha value, plus this is one component of my updated base, plus a part of that will come from 30.0273, and this will be multiplied by 1 minus alpha. So, with this way I will get my updated base value for July 2017. When I multiply this by the seasonal index of August 2016, I will get the forecast of August 2017. But at the same time I will like to update my seasonal index also. I will like to update my seasonal index also, though it will not be used immediately. It will not be used immediately. It will be used for 2018. It will be used for 2018, but I continuously need to update my seasonal index also, and for that purpose this equation will be used of seasonal index, where I get the seasonal index is here, this is dt upon updated ST, which is multiplied by the smoothing constant of seasonality, that is gamma, and this is the T minus L, the seasonality index of the same period one cycle before. This is the seasonality index of the same period one cycle before, T minus L, and this updated trend of July 2017 will be used in year 2018, not now, and we get the updated base value, and we already have the old seasonal index, multiplication of that will give us the forecast for August 2017. So, with this our ratio seasonality model, where we have some kind of seasonal component and this seasonal component is ratio in nature. So, we have got this forecasting of that method. So, we are closing our this session at this end. Now, in our next class we will take this discussion to a more complicated forecasting model, where we will have a trend component as well as seasonality component inbuilt in the same data. Thank you very much.